And it's my pleasure to announce our first speaker of the week, Niki-Myrto Mavraki, who will tell us about both of these exercises, solve points of bifurcations, and geometry and families of rational maps.
Thanks, Harley, and thanks to the organizers for having us all here and for having me speak. And thank you all for coming. So this talk is aimed at non-experts, okay? And I saw Holly gave a preparatory talk last week, and I'm assuming there's going to be some overlap with that too. But feel free to interrupt if you have any questions at any point, okay? So let me say nothing about the title. There are some small points and some bifurcations. And let me start by stating 4 questions that a priori appear unrelated, but we'll see are not. And that for now, I will state informally, okay? And later make precise. So the first 2 questions actually do relate to the small points. And in the first, it's from number theory, and it's about solving equations in roots of unity. So it's asking, let's say that you have a complex plane curve. So curve given by some polynomial equation in 2 variables. And the question is, when does it go through infinitely many points with both coordinates roots of unity? Can you read everything? Please also interrupt me if you cannot read anything. Okay. So question, meaning can we find the equations or say something about them? Okay. The second question is about common pre-periodic points, and it's more dynamical. So now I'm gonna fix 2 degree D maps, okay, in RAD-D. So they're rational functions over C, so polynomial over polynomial with maximum degree D of numerator and denominator. And the question is, when do they have infinitely many common pre-periodic points? Okay. Now, the next 2 questions are about bifurcations. 3. So now I'm not going to fix just one rational function, but I'm going to take a family of rational functions, say parameterized by a curve. Okay? I'll stay simple in this mini course. So I'll have some curve. It doesn't have to be projective, compact. And on each fiber, I have a P1 and a rational function ft acting on it, say of degree D. So f from B to itself is what I'll call an algebraic family of degree D maps. Algebraic because, okay, B will be an algebraic curve. Although it doesn't have to, yeah, it's projective, yeah. Okay, so again, for every parameter T in B, this acts like the specialized map F sub T. Okay, you fix that, and having that, we're gonna see, if you haven't seen before, there is a fiber-wise green current. So that at each fiber, the slice is the invariant measure of the specialized map. And we fix also a mark point from B to P1, some rational map. Okay, and the question is, when is this current 0 when restricted to the graph of the marked point. Okay, so the marked point is here, say, some function A from B to the total space, giving a curve, and here in every fiber you have A sub t. Yes.
Sorry, I'm not exactly sure how much everybody.
I'm not assuming you know it. It's just to give the questions. And yeah, I said it's going to be informal at first. I'm making more formal, but we're going to return to all of this and define things. Thank you. I'm glad also that it's expected because I thought I was preparing too basic stuff. Great. But yeah, we'll return. Okay, now just to see the flavor. This is a complex question on bifurcations. And the fourth question that I don't have time, space to write, but I'll fit it here, is, okay, now you have two families of maps, and it's when is the weights of these two bifurcations, of these two fiber weights going current 0? Okay, which is, yeah. So we'll keep the questions in mind. If you don't understand them, they will make sense. Just to give you the outline of the talks, the point will be to make sense of these questions, place them in the literature, and understand how they are all secretly about the same problem, and how maybe one can use techniques from answering the second question to answer the fourth question once we know the answer to the third question. And then also how maybe we can use the fourth question, the answer to the fourth question, to get a refined answer to the second question and to understand better the geometry of maps that share infinitely many common preperiodic points. Okay, yes?
That is not happening.
Yes, the graph of A. Yeah, thank you. Graph of A, so literally the graph of A. Yeah, so now I will begin. But you can keep this again. If I don't go through these questions, you have to ask me in the end. You didn't explain this, you promised. Okay. Right, starting with the first question. Arithmetic. Okay, the first question is concrete, so hopefully it makes sense to people. I'm asking for polynomials into variables for which you can solve them with infinitely many roots of unity. Any examples that come to mind?
X squared equals y.
X squared equals to y. Yes. What happens here? If y is a root of unity, x is automatically a root of unity. Other examples. X, yeah. Yeah, I can write them like in that form too. Exactly. So, okay, we're done. You gave me all the examples. That's a theorem. So this theorem was published by Lang in 1965, but the proofs were given to Lang independently by Ihar, Asser, and Tate. And says, okay, I'll repeat the statement. C irreducible curve in C square. The following are equivalent. Yeah, this means the following are equivalent. My students keep asking me, but first, the curve goes through infinitely many points with coordinates of unity. And second, the curve is a component of the zero locus of the form x to the n, y to the m is omega, where n and m are integers, not both 0. And omega is a root of unity. Which is, okay, I can, omega is allowed to be an integer, so the m I can put on the other side as well. That's kind of the form you are giving me. Maybe I should have stuck to that. Yes. Okay. This opened a long story and came from a long story. Lang in his paper talks about questions that were posed to him by Manning and by Mumford, also independently, and then formulates many general versions about in a billion varieties that we will not talk about. But we can extract already some philosophy here. Okay, there is something that people call special, and I'll inherit that word, about these points. They are torsion points for a group, for the square of the multiplicative group. So points of finite order, right? So these are special points, torsion in C star square. And there is also something special about these curves in the conclusion. And if there was no omega here, you see that their points form a group themselves. Exercise. Now with the omega, it just translates of a group. So it's like, again, special curves. I'll say torsion translates of subgroups. Okay. So the moral philosophy that we'll keep in mind, it's if a curve that goes through infinitely many special points, then it's special. Okay. But okay, this is dynamics, more dynamical thematic semester than arithmetic. And so we have to rethink about this question and see where is the dynamics. Okay, and we'll look again at this set of special points to do that. And notice that, well, what's a root of unity, right? It's a pre-periodic point for a power map. So, okay, this set is exactly the set of pre-periodic points for the map on C cross C, sending Z comma W to some Z to the D, W to the D. Okay, it depends where you define the map. If you do it on the Riemann sphere, this equality is not exactly correct because you get infinity and you also have 0, but okay, pretty much the same. Okay, and even these special curves exercise, these are also pre-periodic curves for this same map. Okay, now that you see this, you understand that we cannot stop here. We have to take other maps, right? Okay, at least easy ones like FG, which we call split maps. So, okay, it's only 2 boards. Let's see. What about the intersection of a plane curve again with pre-periodic points of a map that I write as f comma g, okay, which is, can you see here? I don't know if I'm writing too much. Okay, and now define it on the product of two Riemann spheres, which I write as P1 because I'm from arithmetic, but it is Riemann sphere. And it maps ZW acting independently with F on Z and with G on W.
For all possible.
Thank you. I should have said, oh, and I see omega and W are the same. Sorry. So when I say the curve is periodic, I mean as a set. So you iterate the set of points giving the curve, and it goes back to a previous iterate of the set. Is that the question?
I'm just wondering whether this point holds for a single map, Z W goes to Z to the D, W to the D, or are you taking also other powers?
Oh, like D doesn't.
You need other powers too, depending on the order of the root of unity.
Can you
That kind of map, sorry, yes. Sorry, yes. Square works, 3 works, sorry. You can also multiply by root of unity. Yes. Sorry, I thought you meant that the curve has to be fixed, but it doesn't. Yeah, any other questions? Maybe now it's a good point. Because we're done with the first question and almost saw how it relates to the second question. So, okay, maybe we almost, let's complete seeing that. So, okay, the question is now, what happens? Can you characterize a curve that contain infinitely many points for this map that acts independently on 2 coordinates, right? And for simplicity, and for this week, we'll focus on the case where the curve is the diagonal line. So what does it mean that the diagonal line contains infinitely many periodic points? It's exactly saying that these 2 maps have infinitely many common periodic points. Okay. So from Lang, we came to the second question. Okay. Maybe today, I thought I'm going to have time to talk about 3, but maybe we'll focus on 1 and 2. I'm going to erase all the questions now. Oh, it's already like 10:20, yes. Okay, of course, there's some experts in the audience, and there are many people who have worked on these questions. I haven't said anything about the literature. This is not my idea. And the collection of problems generalizing Lang's theorem are, in number theory, are called Manning-Mumford problems, or the Manning-Mumford conjecture. Okay? So Lang's result was generalized to a billion varieties. This has been proven in several ways, first by Raynaud in 1983. The proofs are much more difficult than Lang's result, whose proof is quite elementary, actually. Like an undergrad may be able to read it. But dynamically, when considering these split maps or other maps, the question was posed by Tu Zhang and was called the dynamical Manning-Mumford conjecture. Which I write as DMM. And, well, Zhang didn't only consider these maps. Why? You can take any maps. Well, he didn't take any maps altogether, but any maps that have some polarization. Or, if you want, just any algebraic endomorphism of Pn. Okay? So I'll state it as a question, but then move on. So an endomorphism of Pn, meaning it's given by homogeneous n plus 1, say degree d at least 2 homogeneous polynomials. Okay, and he asked when does any subvariety contain a Zariski dense set of p preperiodic points. Okay, maybe you have forgotten the Zariski topology or you never saw it. So if X is a curve, then this just means an infinite set of preperiodic points. If not, the closed set in the Zariski topology are zeros of equations given by polynomials. Okay? So it's kind of a weak topology. A Zariski closed is Euclidean closed, but not the other way. But it's our way to say many points here. Okay. And he conjectured actually that X has to be phi periodic, which turned out is not exactly true, but is maybe almost true. Maybe because we barely know anything about this conjecture. We know only the cases that come, say, from maps extending endomorphisms of abelian varieties, which was already Raynaud's results on the classical Mann-Mumford conjecture. We know cases of maps that come by extending maps given like this, split maps. Okay? And here you may think I'm cheating because those maps are defined on P1 cross P1, not on Pn. But it's an observation of accrued in that you can always extend them to here. I think P3 works. Embed into P3 with a Segre embedding, and the map extends to another map there. Okay, so we know that. And more recently, Dujardin, Favre dealt with some polynomial endomorphisms of P2 and some curves with a condition. Okay, but that's all we know, pretty much. And I don't want to spend forever talking about the literature, but so I'll return back to the problem at hand. Because I want to teach you something about proofs as well in this mini course. Where's the eraser? Oh. Okay, this was a long parenthesis. Okay, so back to the diagonal and the second question. Now we'll write as a theorem, which I'll attribute to several people. But okay, we were asking when does a diagonal contain infinitely many points that are preperiodic for f comma g. Whenever I write f and g, for now it will be just degree d maps, d at least 2. I'm being vague on where they're defined over, but let's say over C, unless I say otherwise. Okay. Okay. Any ideas of examples? Again? F equals, yes, F equals G. Is that what you said? Yeah? Yes. Okay. Yes, F equals Z. F equals Z to the N. Okay. That example will not appear, even though it could, because I'm taking both of them to have degree D.
So generally,
But it's a good example, so I can modify it. I can write F to the N is G to the N. Or you can write some things like, maybe if you have a symmetry of the Julia set, you can compose by a symmetry. And it turns out there are other examples, but okay, but what can we say? Well, we can say in all the examples, the set of pre-periodic points of these two maps will be the same. And we can also say that, similar to the conclusion in Lang's theorem, the diagonal curve, okay, will be pre-periodic with f comma g. Okay. And here, okay, maybe I'm lying. We cannot say exactly that because there are some examples that are kind of weird coming from lattice maps that relate to elliptic curves, which just happen to commute with many things. So, okay, pre-periodic is not exactly true. It has to be pre-periodic for something that maybe commutes with this. Vaguely. Don't focus on that so much. Yes?
Assume that F and G are not special and they are not lattice.
Yeah, if I throw away these cases, then this doesn't happen. Correct. If I assume that f and g don't come from elliptic curves, it's pre-periodic. Okay? Later on, I want kind of that case, the exceptional cases are kind of instructive in arguments, so I don't want to completely forget them, but you can forget them for now. Okay, special. But I'll write from now on f related to g for this relation. So that's kind of the spirit you want to have. Even though we don't exactly know the best way to write down the possible relations, outside of polynomials perhaps, they're still related. Okay, and maybe some attributions. So this looks like, I mean, it is a theorem about maps over C, but it was not proven over C to begin with. It started for maps over Q bar, I believe in my Mars thesis. And later, Joka, Tucker, and Zhang, I saw this morning, they explain how to prove this result over Q bar in a paper correcting the original Manning-Mumford conjecture. Okay. And over C, it was extended by Baker DeMarco. And also by Huan and Zhang. Yes, let's say it like that. Okay. Any questions about the statement? Okay. Now, yes, the topic was some small points and some bifurcations. And in the two questions related to bifurcations, you saw some currents or some measures appearing. And how are measures coming into this theorem? Okay? Let's try to understand how do measures appear in this theorem and which measures say, okay, question, how does this relate to the maybe invariant measure, F invariant measure, or the method of maximal entropy of F and G. Okay. So I'm going to take the next 10 minutes maybe to explain this. I suppose you all have seen this measure. Supporting the Julia set. Yes. It just doesn't charge points, and it's invariant in the sense that the pullback of distributions satisfies this relation. Okay, but to explain this, I need to talk about a concept from number theory, the height. Okay. Oh, I left the eraser up there. Thank you. Thank you, thank you. But they're not magnetic. I'll get that later. Okay, heights. They're from number theory, so they are associated first, say, to rational numbers. Okay, what's the height of a rational number? A over b, so now a and b are integers, and they are relatively prime. The height is essentially the number of bits I need to store this number. So it's a logarithm of the maximum of the absolute value of a and b. Okay? And you can write this in several ways, actually, that are useful for us. You can see, okay. Well, what are the absolute values one can put in the rational numbers? You have the standard absolute value, and you also have the p-adic absolute values associated to primes, and that's all, right, by Ostrovsky. And you can use these absolute values to write down this quantity by saying that it's just the sum over all primes of log plus, which is the logarithm of the maximum of 1 and a over b. Okay, sub b. Okay, plus the usual one. And maybe if you haven't seen heights and this looks weird, forget about it, but look at this function log plus. Log plus as a function of the complex numbers now. Its Laplacian, in the generalized sense, is exactly the Haar measure in the unit circle. Right? So it relates to a measure already. Okay. And now you can take me on some faith that you can extend this definition to all algebraic numbers.
I'm sorry for the interruption again. So log plus is like maximum between 0 and log. And what can you just remind me what the absolute value, I mean, the absolute respect to p is?
Yes, okay. And then it's an exercise with the prime factorization. So a over b sub p is, let's say, q sub p is q, let me write it like that. P to the n, a over b, where p doesn't divide a or b, okay? It's just p to the negative n. So it decays when the number is very divisible by p. And it grows when there's a big power of p in the denominator. Yes. It's an absolute value. In fact, it satisfies better than the triangular inequality. All triangles are isosceles in this topology. And it's fun and easier to play with than the complex numbers. Yes?
You said something with the Haar measure and the
Yes. Yes. The Laplacian, meaning DDC of this is the Haar measure on the unit circle. Okay, maybe it depends how you normalize things, but let's pretend with the correct normalization. What else do I want to say? Oh, I said you can extend it to the algebraic numbers, for which, well, here you have to take more some faith. There is some number theory to extend these absolute values to any finite extension of Q. But once you do that, and you have an algebraic number, then the height of alpha will be kind of the normalized with the degree of alpha. Oh. Okay, I'll write the degree of alpha. Okay, here I hope Holly talked about all these things a little bit. Sum over log plus alpha. Similar formula. Okay, you need to scale them maybe a little bit. let's say here, places, vaguely. And the degree of alpha is kind of the degree of the minimal polynomial of alpha over Q, which you can also use to define this height by looking at the zeros of the minimal polynomial and averaging out all the ones that are outside of the unit circle, plus the leading term. Anyway, you have a height. What to remember about this is that it relates to these absolute values, and maybe another thing to remember is called the Northrop property that says that it's a good way to count algebraic numbers, because the set of algebraic numbers with bounded height and bounded degree is finite. Okay, exercise. over the rational numbers, it's easy to see it. You just constrain both the numerator and the denominator. That's what the height does. The degree is 1, you constrain them, you get a finite set. But it works in general. And maybe the second thing to remember, coming straight away from this property, is that the height vanishes if and only if alpha is a root of unity. Okay. Again, I'm lying a little bit, or 0 or infinity, if you want, but that's it. Yeah, I was back here. Places. It's kind of the absolute values living on an extension of Q containing alpha, extending these ones that we have here. Yeah, it's vague. You don't have to worry about it. Something like this and this. This and this. Okay. Yeah, it runs exactly at the root of unity. You can prove this dynamically a little bit. Hint, take all the powers of a root of unity. They form an a priori infinite set of bounded degree. Yeah, that's a hint. Okay, but I want to go to dynamics, and time is running out. So maybe the third property is that takes some proof, is that if I have now a rational function defined over Q bar, right? And I plug in the height the iterate of a point, then I can see how it grows. It grows like d times the height of a point plus some error term that depends only on f. Okay? This means that the absolute value of the difference of these quantities is bounded by a quantity depending on f. The big O of 1. Okay? And having this was done, I guess, by Cole and Silverman, but also at around the same time through a different approach by Su Zhang. You can define what I'll call the canonical height of a rational map, denoted as h hat ff alpha, to be the limit as n goes to infinity of the height of the iterates of alpha divided by the degree to the m. Okay. This is the canonical height. Right? A priori, this limit doesn't have to exist, but because of this property, if one proves it, it follows that this limit makes sense, and it is some non-negative number that looks like it's trying to measure the arithmetic complexity of an orbit. Okay? What else does it satisfy? Okay, why am I talking about it all the time? Let's go up. Or maybe an equivalent way to define this quantity is to take first this equation. So because we took all this limit, then we killed this O1 error term for the veil height. So we get an exact equation, which is probably why they call it canonical height. And second, that it relates to the veil height in the sense that it differs from the veil height by a bounded amount, again, like before. Okay. Sorry? Oh. Yes, thank you, thank you. Okay, but maybe none of this is so important to remember. What you should remember is that it sees our dynamically special points. It becomes 0 exactly when alpha is pre-periodic forever. Exercise. Okay, and now back to the measures and where they're coming from. And this goes back to an so-called arithmetic equidistribution theorem, maybe. That, okay, has been proven by many people. I believe the versional state was already first done by OTCR. Balonta taught me that. But it was also done later by Baker-Amley, Favre, Rivera-Letelier, Huan Zhang, Xemperlois, Tuillier. Many people. Hope I didn't forget somebody who is watching or is here. But with various proofs. Okay, basically 2 proof strategies. One is based on potential theory, and the other is based on Arakelov intersection theory. And it says that, okay, suppose I take an infinite sequence of pre-periodic points, or more generally, back to the title, small points, which means points that may not have 0 canonical height, but whose canonical height tends to 0. Okay, so let alpha n be, let's say, a non-repeating sequence of points with canonical height tending to 0. Okay. Then the conclusion is that the discrete measure that is equally supported on their Galois conjugates converges to the F invariant measure weakly. Meaning, okay, then, okay, let's write it here. So this is a Dirac measure. This is the Galois conjugate of alpha n. And this is like normalized by the degree. Converges to mu f. Okay, in the sense that for any continuous function, the average of its values on this Galois orbit converts to the integral against this invariant measure. Okay. So what does it say? So it takes this arithmetic things, Galois orbits, which are like all the zeros of the minimal polynomial of alpha n, right? It's an arithmetic quantity, but it says that its geometry can be understood through this invariant measure. So the points will kind of accumulate near the Julia set of this map. Okay? If you have not seen anything like this before, I'm sure you have. In complex dynamics, like if I took all the pre-images of, say, non-exceptional points, then it was known that all of them together equidistribute. Here, pre-images have height that is small, going to 0, and this says that you don't need to take all of the pre-images together. It just suffices to take their Galois orbits, and they'll still equidistribute. Or similarly, you don't need to take all the n periodic points, and you still get equidistribution. So it generalizes, in a sense, the results of Brolin, Lubitz, Magnesa, Sullivan. Okay, what time is it? I see. Any question first? Okay. So how does this relate? Oh, maybe one more thing that I didn't say. It's important. In all the proofs, right, why I did all this height stuff, kind of the height already relates to the measure. And that appears in the proof, in the proofs. In the sense, just like we had the veil height written as this sum of log pluses, the canonical height of, say, a polynomial is written also as a sum of, what do you use for green functions? The green function of the polynomial. Okay. Say the escape rate. So many names. Yeah. Literally the escape rate, if f is a polynomial. Okay. Yes, I want the subscript. Say v and say v. Okay. And again, the Laplacian of this normalized property would be this. And for rational maps, I can also write this quantity. Later on, I will sit and do it, even though I'm lazy to concretely do it, because you need to lift the rational map to a map of C square and to lift your points. So I will use this notation, lift, lift.
What is the effect of taking a single place union?
The effect of
I mean, what is the effect of the sum? Like, what are you summing over?
Sorry. Yes, all the places. So, okay, but if everything's over Q, it could be, right? I'm summing over all the primes, ZP, plus the usual one. This is a complex one that you knew. And the places appear here, so I didn't write it correctly. Yes.
So I think Polly called them absolute value sets.
Yeah.
Yes, so it's a different absolute value. Yes, so here we write infinity for the usual one. Okay, where are we? Yes, so maybe you now see how we can prove the theorem. Maybe at least over Q bar. Oh, and here I should have said, maybe I did. It's important for this statement at least that f is defined over the algebraic numbers, the way I wrote it. Although it's not that important, and we will use generalizations of the statement later where f is not defined over the algebraic numbers. It's a beautiful proof. Maybe if you are curious, you can read, there's a paper of Ramley that is very readable, explaining how this works for the veil height. Okay. But now, let's see how it relates to our theorem, sorry. What we were wondering, when do two maps have infinitely many common pre-periodic points? Okay, suppose that you have an infinite sequence of common pre-periodic points. Okay, then both of the canonical heights with respect to f and with respect to g, okay, will be 0. So their Galois orbits will have to equidistribute with both mu f and mu g, which in return now have to be the same. This is a measure rigidity question that had been studied by many people, starting from polynomial cases where we know even more things about maps which are Julia sets, to rational maps. I guess the best result available is by Levin-Psitsky, LP, which then will imply by itself that what we wanted, that f is related to g. So that kind of completes the proof over Q bar. And then you have to extend two maps over C. There's maybe a couple of ways to do it. Conceptually, what you want to do is to take two maps defined over C, say they are E z square and E plus 1 z square plus 5. Bad examples. But then you want to think of them as E is a transcendental number. So you want to think of it as a transcendental parameter T, which can be varied over the complex numbers in itself. Okay. And then you need to explain that if the original E maps have infinitely many common preperiodic points, then for many algebraic T, these specializations will also have infinitely many. So then you can use this result and pass to the limit because these measures are continuous. And with the rigidity, again, conclude over the complex numbers. That's a very vague idea, which needs work. Okay. Maybe I have 2 minutes. I was told it's 50 minutes or an hour, anything I want. Thank you. I want to say 2 things. First, we did not only prove this, we proved something stronger. Aye. And that will be important for problem 3 and problem 4. So we proved that two maps having a common sequence of small points have to be related. So in other words, we proved, okay, I'll write S mean of the canonical height sum to be the essential minimum, meaning the infimum if I throw away finite sets. Okay? So we prove that this is 0 if and only if f is related to g. Okay. This kind of question was known as a Bogomolov type problem, generalizing many Mumford type problems. And even for the case of the square map, like in Lang's theorem, there is no completely elementary proof, let's say, of this Bogomolov type result. But still, yeah, here we got it. And maybe the last thing I want to say, because that will tie us to the next 2 days, it's also known by Zhang, okay, Zhang fundamental inequality. Fundamental inequality, that this essential minimum is 0 if and only if a height is 0, the canonical height of the diagonal. This is not crazy hard to define. Okay, if you try to do Zhang's definition, it's going to take forever. But his definition works better for many things, but I'm not going to introduce you to that today. An easy definition is one we have already seen, because we have the height of a point, and we can use the height of a point definition to define height of points in Pn in exactly the same way. So we can define, okay, if X is a subvariety of Pn, you can define the height of a subvariety, okay, I'll write it height hat, to be, well, the height of a certain form defining the subvariety, like a form whose zeros define subvariety. It's like the Chow form over, say, the degree of X. Okay, too much algebra. Suppose that X is a curve or a hypersurface, then this is just the height of the coefficients of the equation defining the hypersurface. Right? This is the degree also of the hypersurface, if you want. Okay? And then you can take the canonical height, just so you have one definition in mind. Here you have a map, phi acting here, and you can define the canonical height of X to be the limit 1 over d to the n of this height of the iterates. This definition is coming from Philippon's work, and later David and Philippons and Ben Hood's, and was not so commonly used in dynamics. But at least to have something concrete in mind, that this makes sense. So next time, we will start thinking of this question, of when is this height 0, in the case that the maps are defined over a function field, not necessarily the algebraic numbers, and tie it back into our bifurcation questions, though that may take more than one lecture. So I'll stop here for today.
Any additional questions from you, Bob?
In the proof that you outlined, showing that if you have two maps that share infinitely many periodic points, they have to be related. The argument seems to show that also if they just have a sequence of points of shrinking heights, then they have to be related. Is there a way to interpret points of small height to like understand what that's saying?
There's many points of small height you can write. You mean how to think about them? Yeah. Maybe the theorem is telling you how to think about them and geometrically speaking, right? They go to this measure. But okay, as examples, I mentioned in words, but I didn't write it. If you look at pre-images, Fn alpha equals beta, this will have small height. Okay, maybe you can write the height, use a property that the height of the iterate is the degree to the n times the height of alpha is the height of beta. So then divide by d to the n, and you see that this canonical height of alpha is small. Right? This is an example. And then you can start trying to write other potential equations defining small points.
If I can relate, because you had asked a question last week. I think one more natural way from the complex perspective, once you're comfortable with the idea of lots of these different absolute values, is that having small height means that you're close to your polynomial. It means that you're close to the Phillips set for every choice of absolute value. And so having small height for both of them would somehow mean that you have this large collection, this infinite collections of QBs.
Thank you, Holly. Yes. Yes, that's kind of what the theorem is trying to answer, right? What can you say? And it's not over. Maybe there's more, but.
Is there an example that you can explicitly calculate non-zero canonical height?
Non-zero canonical height? Yeah, explicitly. It's very hard to compute heights, but let's see if I don't get stuck. Non-zero, here, pretty if beta is not pre-periodic. Okay, 0, sorry, yeah, your question is simpler than I thought. The zeros are exactly the pre-periodic points, right? Perfect, so all you have to do is write an example of a point that's not pre-periodic.
Yeah.
But, you mean by computing it? So this is probably a good question.
You do it for the power.
They have tried to write code. The problem is that you iterate a lot, and the logarithm has an error, and every time the logarithm has an error, you iterate, it gets to have a bigger error. It's hard to compute. To give you an example, in elliptic curves, these heights were known long before they were introduced for the basic problem. Anyway, we don't even know if the elliptic curve, where there's many more tools to compute, we don't know if this gives an algebraic number, an irrational number, and what kind of numbers it gives.
If you do like f, so that's an example like f equals z squared plus 1, and you start with like 1, don't you like at least show it's not going to be 0?
Oh, I can show you one example that is. Yeah, I can take an example that grows, for example, in the complex place, right? If I take, if I'm outside of the Julia set, say if I have a polynomial, right, and I take z big enough so that it's outside of the Julia set, then it will grow, right? It will grow in the complex place, and so the total canonical height will be definitely positive because it's bigger than the contribution of the complex place. Okay, what am I saying? Height, okay, for polynomials, it's easier. Thank you, Sina. Right? It's at least, yeah. I'm lying a little bit, but yeah, you can compare it with the complex contribution. Okay, thank you, Thomas. Yes, I'm trying to be most general as possible. Yes, everything over Q, I'm not lying. The canonical height is at least the complex escape rate, which you can draw the pictures of values where it's positive. And it's computable. As soon as, okay, alpha is big enough.
Yeah, by the theorem, we know that already know that if alpha is not periodic, then it's positive. So,
Correct.
I was wondering if there's an example of this we can get with exactly non-zero.
Expectation is transcendent in sex. The powering map, you're just taking like log of an integer. Right? That's not something you can do anything better than approximate.
Thanks.
Yeah, even for the Veil height, there were questions like that. I think Gabriel Dill, in his thesis, wrote a chapter on, for the Veil height, its values. And if you can compute which intervals contain most of them. And
I mean, it's even worse than that somehow. Like, it's a theorem that, unless we did some